When a company switches the relational database that it uses, you wouldn't expect the news of that switch to go viral. Most engineers are not interested in the subtle differences between MySQL and Postgres, right? Uber recently switched from Postgres as its main relational database to using MySQL. Evan Klitzke is today's guest, and he wrote a detailed blog post about this switch. And the post got very popular for at least 3 reasons that I can think of. One, Evan is a great writer, and he describes these complicated distributed database concepts in simple terms, which he also does in this episode. 2, Uber is a very interesting company with high-quality engineers. It has unique engineering challenges and database attributes that we get into in this episode. And when Uber takes on a task that requires lots of work, like changing its default relational database, people do pay attention, even if it's a somewhat subtle niche engineering topic. And the third reason is that MySQL versus Postgres sounds like the type of divisive topic that people should get emotional about, for the same reason that people get tribalistic about React.js versus AngularJS, or Kubernetes versus Mesos, and so on. These debates are typically not worth getting as tribalistic and divisive as people tend to do, but nonetheless, they do get tribalistic about them. If you are even slightly interested in distributed systems or databases, I highly recommend reading Evan's blog post in detail. It's such a great read and such a great explanation of the same issues that we get into on this podcast episode. So I hope you enjoy this episode, and it was a great treat for me. So thanks to Evan. Let's get into Uber's switch from Postgres to MySQL. DreamHost Cloud gives you fast virtual machines and storage for a low price. DreamHost Cloud brings infrastructure as a service together with 24/7 support and a great community. The DreamHost Cloud platform is all based on open source code that uses OpenStack and Ceph. Go to dreamhost.com/sedaily to deploy your application today and support Software Engineering Daily. With the easy-to-use UI, standard API, and a powerful SSD infrastructure backend, DreamHost Cloud has everything that you need to deploy and maintain your application. The billing for virtual machines is simple. Only 600 hours are billed max per VM per month, with 100 gigabytes block storage included, and free bandwidth for a limited time. It's easy to try at dreamhost.com/sedaily. Deploy your application to DreamHost Cloud today. I know you've got that side project waiting for its deployment, and when you decide to deploy it, check out DreamHost at dreamhost.com/sedaily. Thanks to DreamHost for being a sponsor of Software Engineering Daily. Now let's get on with this episode. Evan Klitzke is a software engineer at Uber. He recently wrote about Uber's migration from Postgres to MySQL. Evan, welcome to Software Engineering Daily.
Thanks for having me, Jeff.
Let's start off by talking about Uber's database workloads in the abstract. What are the ways in which Uber's database workloads are unique?
I think that our database workloads are actually pretty similar to most other people's database workloads. We generally have the same requirements as other people. The one thing that might be a little bit different is that we have a pretty high write-to-read ratio. And what I mean by that is when people open the Uber app, they're generally opening it so that they can take a trip. And when they take a trip, that requires writing to the database. And so a lot of other people have like lots of reads happening, and we have more writes happening.
I see. So in contrast with something like Facebook, where you have to read all this data in order to load the news feed, or Twitter to load all your tweets, there's not as much of that in Uber. Okay. So what does Uber need from a relational database?
So again, we have kind of the same requirements as other people. We want something that's powerful, that has like good high availability features, and is fast. And so I don't think that our needs are actually that unique.
Okay. What kind of data is stored in those relational databases?
So in the relational backend, we've got all of the trip information, client information, driver information, like metadata about cities, that type of stuff.
Okay. Do you have other types of databases, or do you use exclusively relational databases?
Yeah, we've got a lot of different databases. So we've got other types of databases where we use more for caching information. So for instance, like in the real-time dispatching system, we persist like the state of jobs and stuff that are happening. But our relational databases, what they're generally storing is they're storing this business information, so like trip information and user information.
A place like Uber has a bunch of different teams that are working independently on a variety of different services. Is there a need to standardize on a specific relational database, or can you just say, all right, every team can do whatever they want as long as their service meets this SLA? We don't care what database they're using.
Yeah, so we do let people choose the database that they want depending on their use case. However, if their service is going to have a certain load, then we require that it be one of a few things. And the reason for that is because from an operational perspective, it's easier to guarantee developers here that we can give them the support that they need for the scale that they need if it's one of a few things that we understand really well.
So you do want to standardize on a specific relational database.
Yeah, that's right. So if the scale is at a certain point, we require that they be on MySQL or kind of our in-house thing, schemaless. And there are some other use cases that we have, but yeah, we do require that they fit into one of a certain number of databases.
Okay. Before we get to talking about Postgres and MySQL in the gratuitous detail that you wrote about them in, there's a feature of relational databases called multi-version concurrency control that I'd like to level set by discussing a little bit. What is multi-version concurrency control?
So multi-version concurrency control, it's also called Mvcc, which is just the initialism for it. It refers to the property that you can have different versions of the data in the database, and there might be different transactions in the database that see different versions of something. So there's multiple versions of data, and concurrently, different things can see different versions.
What types of problems does that Mvcc solve?
So what Mvcc gives you is it gives you stronger consistency in the database in the sense that if you have a transaction that's running, you're guaranteed that it will have a consistent view of the data throughout the transaction. And that just kind of makes the burden for a developer a little bit easier to reason about. So an example would be if you've got a transaction open that's viewed user information out of a user row, you're guaranteed that for the course of that transaction, that information won't change. Like the user won't get deleted, it won't be changing in some unexpected way. And so it generally makes it easier to reason about the database.
Okay. And what kinds of data structures do we need in our database to implement multi-version concurrency control?
So what you need is a version for every row, and you need for each transaction, you need to know the maximum version that it's allowed to see.
Okay. So we'll come back to Mvcc, but let's start to talk about the selection of databases. Why did Uber initially choose Postgres for its relational database?
So we actually didn't initially choose Postgres. When I started the company 4 years ago, we were using MySQL, and the reason that we decided to switch to Postgres at that time was Postgres had better support for online schema changes. So the problem that we were running into was that we had these pretty big databases, and then we'd need to like add a column to a table, or we'd need to add a new index to a table. And MySQL had pretty poor support for doing that while the database was online. And Postgres had really good support for that. And so there are a number of reasons that we changed, but I would say that was the most important one.
So you had a rapidly evolving schema, and Postgres was better than MySQL for that rapid schema evolution.
Yeah, exactly.
Okay. So has Uber's architecture evolved significantly since that choice of Postgres? Have you settled on the type of schema that you need so that you don't need that rapid schema update feature as much anymore?
We still have that requirement. There's a lot of developers at Uber who are developing all kinds of things. And lots of times they don't know at the beginning what schema they need, or they think they know what schema they need, and it changes over time. So that's still a requirement that we have.
So it's still a requirement. I guess we'll get into how you deal with that today. Is your ability to deal with that is probably related to schemaless?
Yeah, it's partially schemaless and partially that there are other tools that like don't come with MySQL, but that are like broadly used in the community that assist in this online schema change.
Okay, all right. Well, we'll get into those later on, but what were the limitations that you began to encounter with Postgres? So you started with MySQL, you said, okay, we need more rapid schema evolution, we're switching to Postgres, and then more recently, you've made this blog post where, oops, we need to switch to MySQL. What were those limitations that you began to encounter with Postgres?
So the main limitation that we encountered kind of right off the bat was worse performance, and that came in a number of ways. So when we switched from MySQL to Postgres, we did it by adding more total database servers under Postgres, and they were more powerful database servers. And we weren't getting the performance that we wanted. In fact, we were getting worse performance with our MySQL cluster initially. And we had to correct that by adding more servers. So we got worse performance, and we also had worse connection scalability. So having the backend create lots of connections to the database, even if those connections were idle a lot of the time, that had higher overhead than we were hoping that we would get.
So as we get to talking about why that is, in Postgres, row data is immutable, and it will become evident why this is relevant to the conversation. But could you first explain what that means? What does it mean to have immutable row data in a database?
Yeah, so Postgres calls its rows tuples, and they're generally mutable. And so what that means is if you have a row and the row needs to update for some reason, like you've got an update statement that runs in the database that's going to change a row. Instead of actually changing the row on disk, generally what Postgres will do is it will create a new copy of the row, a new tuple. And so it's immutable because rather than changing the old row, typically what happens is a new row is created that's a copy of the old row plus the changes that need to be applied to it.
Can you give an example of some instances where you could have multiple versions of the same row?
So almost any time that you do an update to a row, a new copy of the row will be created. There's an exception called heap-only tuples, but that's kind of a corner case. So typically what happens is you've got a row, you do an update, a new version is created, so now there's two versions. You've got the old version, and you've got the new version. And that old version will persist for as long as there are transactions that need to reference the old row for Mvcc purposes, or until the auto vacuum process runs in the database. So you'll have it either when there's Mvcc or when vacuuming hasn't yet happened in the database.
Okay, so this ties back to our earlier definition of Mvcc. How does this idea of making immutable row data, why is this related to Mvcc?
So the way that it's related to Mvcc is that when there are multiple transactions open that need to see different versions of data, they will reference different versions of this row. So these multiple row versions are closely related to the concept that you've got different transactions running that need to see different snapshots of data at different points in time.
And you also mentioned this term vacuuming. What is that?
So vacuuming is a compaction process that happens in Postgres. So what would happen is, let's say you didn't have vacuuming at all. Every time you updated a row, you'd get a new copy of it. And then eventually you'd have all these old copies of rows, and they would be taking up space in the database. And your database would get really, really big over time. Like eventually you'd run out of disk space. So vacuuming is a process where the database goes through, it finds old versions of rows that are no longer referenced by anything, and then reclaims the space that those rows take up.
Okay, so it's a garbage collection process. You basically say, okay, there's no more processes that are ever going to want to access this old version of the row. We can garbage collect it and move on with our life.
Yeah, that's exactly right.
Okay, so these different versions of a row in Postgres have a CTID, which is, if I understand correctly, kind of like a version number. Is that accurate?
It's not exactly a version number. What the CTID is it's a way to refer to like exactly where on disk something is. So what the CTID encodes is it codes what file in the database this row data is stored in, and then essentially what offset within the file something is at. So the CTID is what Postgres uses to actually locate the copy of a row.
I see. Okay. So in what ways does this strategy of tracking the row with CTID, how does this negatively impact performance?
So there's nothing ipso facto wrong with using CTIDs to locate rows. The problem that we ran into was that secondary indexes in Postgres directly refer to CTIDs, and so when you're changing a row and a new copy of the row is created, that new copy of the row will have a new CTID, and all of the secondary indexes for that row will need to be updated to reflect that new CTID. And so that causes this problem that I called in the blog post write amplification.
Okay. And can you give a example for how this problem can occur? How does this secondary index update problem manifest in reality?
Yeah, so let's say you've got a table, and the table has got 10 columns, and we've got 5 indexes over 5 different fields in that table. If you were to change a row, and so you're going to change one column in the row, and that one field in the row is covered by an index. Logically, what you'd expect to happen is, well, we've got to write out the new row data for this new row tuple, and we need to update the secondary index on the field that was actually changed. So that would be 2 logical updates. However, what actually happens is, when this new row is created, the new row has a new CTID, and so all 5 indexes need to be updated to reflect the new CTID. So rather than 2 logical changes, you've got 6 logical changes in this case. And so that requires more writes to be happening to disk, and more activity generally is happening within the database.
Okay, so how often does this occur, or how often was this occurring within Uber's Postgres databases?
So the extent to which this is a problem really depends on how many indexes you have in your tables. So the more indexes you have, the more this write amplification occurs. We had a lot of indexes in our tables. Frankly, we had more indexes generally than we should have had. And that was kind of the result of, we didn't have a lot of people who are database experts, but we had a lot of people writing code. So this was a big problem for us. But if you...
And they wanted fast lookups.
Yeah, exactly. But if you had fewer indexes, or you're a little bit smarter about them, it would be less of an issue.
I see. So, I guess, do you want to define that term write amplification? I mean, I think you've kind of defined it already, but maybe you could just define it so that we have a term definition.
Yeah, so I actually got the term from, this is something that people talk about with SSD disks, and what they're talking about is you want to do like a one byte write to the SSD drive, and instead you have to write out an entire block, so you have to write out, say, 4 kilobytes of data. So you've got 1 byte logical change, and then a 4 kilobyte like physical change that's actually happening. So I kind of appropriated that term, and so what I'm using it to refer to is the fact that you've got a small logical change, and that manifests in a much bigger physical change in terms of the amount of data that needs to be written out to disk.
Okay. So when you identified this problem, I mean, you just mentioned that you could have solved it with, well, you said you could have made it less bad by having fewer indexes. Why didn't you just, cut down on the number of indexes?
We tried to do that, but for one thing, it's generally really scary to drop indexes because, like, you might need the index. What if you drop the index and then everything gets really slow? If you drop an index and then you need to recreate it, recreating the index is a relatively expensive process, so that's difficult to do. And again, we kind of had this problem where there were more people writing code that interacted with the database at the company than people who really knew how to like operate this database and administer it.
Mm-hmm. We should also talk about replication. Postgres has this write-ahead log for database changes that is relevant to the replication process. Can you describe what a write-ahead log does and why it's useful?
So write-ahead logs are useful for any application that needs to be crash resistant. So the idea is you've got some application that needs to be highly consistent in the event of a crash, or let's say there's a power outage, something of that nature. So what you do is you take the changes that you're about to write out to the data space, you write them to a log, and then after you've written them to the log, you actually persist those changes out to disk. And so the reason this is helpful is that in the event of a crash, you can compare what's in the log to what you have in your table space, and then you can kind of reconcile those differences. And so write-ahead logs are generally a feature of crash-resistant applications, and the way that this is related to replication in Postgres is that when replication was added in Postgres 9, they were like, well, we've already got this write-ahead log. It's already writing out all the changes that we're making to the master. And the master needs to have this thing anyway, even if we don't have replication enabled. It needs to have the write-ahead log for crash recovery purposes. And so replicas are implemented in this way where they stream the wall data, and then they apply it as if they're in crash recovery, and therefore they get all of the updates that the master is getting.
And is this replication strategy with the write-ahead log, or the way that Postgres uses the write-ahead log for replication, is this are there some aspects of this that are notable to highlight before we get to sort of the migration process and how this contrasts with MySQL?
Yeah, so the thing to understand about this replication strategy for Postgres is that what's in the replication stream is the physical changes that are happening on disk. So every byte that is changing on the master ends up in the replication log. So if the master is doing lots of little tiny writes to the database, even if a small number of logical changes are happening in the database, that will manifest as a lot of physical changes to disk, and therefore that'll end up as a lot of data in the replication stream.
Okay. So we've talked about write amplification, we've talked about replication. How severe, or what are the problems at the intersection of these two things?
Of the intersection of write amplification and what?
Yeah, so how does write amplification and replication, how do these two the two things, how they manifest in Postgres, how do these lead to problems?
So when you have write amplification, that's causing lots of small physical changes to happen to disk, and so that manifests as lots of data ending up in the replication stream. And so that can cause problems for various reasons, because like the main problem would be if you have limited bandwidth, because of this write amplification thing happening in Postgres, you're going to run up against your bandwidth constraints more quickly, because this write amplification essentially causes the replication stream to be amplified as well.
Okay. So this is a broader question, but when you have a write-ahead log like this, does the write-ahead log itself get replicated also?
It does in Postgres. Other databases do that differently. So MySQL has a slightly different mechanism for replication, but in Postgres, the write-ahead log is what is replicated, and that's how slaves are streaming data from the master.
Got it. So the problem that you're describing here is you say, okay, I want to update the database. The write amplification causes all of your indexes to be updated rather than just a limited subset of those indexes. And then all of those index updates go on the write-ahead log, which just causes the problem to compound further. Is that an accurate depiction?
Yeah, that's pretty accurate.
Okay. So what were the top-level performance issues that this was manifesting in? Like, was this propagating beyond the data layer to users?
Yeah, so the very first problem that we had when we switched to Postgres, besides like the general performance problems we were having, which we kind of mitigated by adding more servers, but we ran into this issue where during peak load, we had difficulty archiving WAL files to S3 fast enough. So we had this disaster recovery strategy where we wanted to make sure that we were retaining all of the WAL files for like 90 days, something like that, in the event of a disaster. And so under peak load, we were writing out these WAL files so quickly that we would sometimes have difficulty getting them up to S3 in a timely manner. And we kind of had the inverse problem where we'd try to restore a database snapshot. And so we'd get the snapshot restored. The slave would be, say, 24 hours behind. And it would take a long time to stream these WAL files from S3 fast enough to get the slave in. And then kind of the last problem that we're having, and this is the one that impacted users, but when we were getting these replication delays, it would cause our delayed task layer to fail for a couple different reasons. One would be if the replication stream was actually delayed. The other would be if there were queries canceled because of this Mvcc problem on the slaves. And so what would happen would be if these tasks get delayed, then they get canceled and they get requeued. And the main one that we cared about from a user experience perspective was billing. So under peak load, what would happen would be billing would get delayed because we get all these database errors. And then we wouldn't bill someone's credit card for, say, like 12 hours, or in some extreme cases, up to 24 hours. And users don't care about that too much because if you take a ride in Uber and your credit card, it takes a while to get billed. Most people don't mind that too much, but drivers really care because we can't pay drivers until we bill the user. And so if we're not processing trips for 12 hours, that means that drivers who expect to have made some money during their shift aren't getting paid in a timely manner, and they're relying on that money for their bills or whatever it is that they're doing in life. And that's something that really impacts them in a negative way.
Wealthfront is an automated investing service that saves you time. As an engineer, your time is valuable. If you want to invest, but you don't want to spend significant time evaluating your portfolio and allocating assets, take a look at Wealthfront. Go to wealthfront.com/SEDaily to open an account today and get a special offer for Software Engineering Daily listeners. $15,000 managed for free when you open your account. With traditional investment services, there are many humans in the loop that are doing things that Wealthfront automates away. When you pay the commissions and account fees of these traditional investment services, you're paying for work that could be done by a computer. So don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/SEDaily. It would support Software Engineering Daily, and it would introduce you to the world of automated investing. Wealthfront.com/SEDaily. Thanks to Wealthfront for being a continued sponsor of the show. Now, let's get on with the show. You mentioned WAL files. That's write-ahead log?
Yeah, that's right.
Interesting. So, and I think you kind of touched on this just now, but you've discussed how write amplification and replication, this problematic overlap becomes particularly severe when we're talking about replication across data centers. So explain why that is.
So the architecture that Uber has currently and at that time was we have a West Coast data center and a co-location facility, and then we had an East Coast data center and a co-location facility, and we've got this link between the two data centers, and the bandwidth on that link is at much more of a premium than bandwidth in geographically close regions. So for instance, we had less bandwidth between the West Coast data center and the East Coast data center than we had between the West Coast data center and then like the Northern California AWS availability zone. And so at peak load, when we're generating lots of these write-ahead log files, we would sometimes have difficulty keeping the replicas on the East Coast up to date with stuff in the master, just because there's less bandwidth. And that's kind of scary because at the time, what we were primarily using that East Coast data center for was disaster recovery. And if the East Coast data center is delayed by several hours, if there's an earthquake or some natural disaster on the West Coast, then we can't rely on that East Coast data center having the data that we need.
So a separate issue beyond this stuff that we're talking about with the write-ahead log and the write amplification and the replication, a separate but related issue is this bug that you ran into in Postgres 9.2 that led to data corruption. And this was a bug. It was not an explicit part of the Postgres feature set, but because of the way that Postgres replicates and then the write amplification, this event alerted you to the idea that a bug in Postgres actually can become unreasonably dangerous. Is that accurate?
Yeah, that's accurate.
Okay, so explain why that is. Like, why did this bug have the potential to corrupt so much of the database hierarchy?
So what happened was we ran into a bug in a particular version of 9.2 where we had promoted a slave to become a master using this timeline switch feature. And in whatever version of Postgres we're using, there was this bug where some of the slaves would either skip or double apply some of the write-ahead log statements. I forget which one, but in either case, the slave would be slightly out of sync with the master. So the way that this would manifest would be you would do select star from users where ID equals 10, and you'd expect to get one row back, and you might get 2 rows back because of these misapplied wall statements. So the reason that this was really scary to us is indexes in a database are organized as a B tree, and occasionally what happens in a B tree is you need to rebalance the nodes. And when you rebalance the nodes, kind of all the internal pointers to things are being shuffled around. So because the write-ahead log happens at this physical layer where it's saying exactly what bytes to be writing out to the database, we are concerned that if there is corrupted data in an index and one of these rebalancing operations happened, it could cause an entire database index to get corrupted. And that would be really scary because that would completely break all the queries on that table.
Okay, so, but this is a problem in every database, right? Doesn't every database have its bugs, and this is just an unavoidable hazard, and you happened to step on a bug at this time when Postgres was having other problems. So I'm just curious why this was something you touched on in the blog post when you're discussing moving from Postgres to MySQL, because it seems like the probability of having a really bad bug in any given database is equal.
Yeah, so it's definitely the case that all databases have bugs, and in fact, anyone who's used MySQL, particularly with MySQL 5.0, they've run into lots of bugs and lots of replication bugs. The thing that made me call this out in the blog post was because replication happens at this physical layer in Postgres, if you have an error in that layer, it has much more potential to completely corrupt the on-disk format of the database. Whereas other databases like MySQL, they do replication more at a logical level. And so there are certainly bugs in MySQL's replication, but in my opinion, those bugs are less likely to manifest as a completely corrupted index or a completely corrupted database.
Got it. So we're still talking about Postgres. Eventually we'll get into MySQL and the migration there. But there were a couple more problems that you dealt with. So there was this issue you had with Postgres with the lack of replica multi-version concurrency support. Explain what that is.
So the way that I think about it is you've got these replicas and they can serve read queries. And so even though you're doing these read queries and they're not modifying data, they still have transactions open if you're in say repeatable read transaction isolation level. So there's still transactions happening on the slaves. And they still need Mvcc even though updates aren't happening. And meanwhile, there's this replication thread and it's applying updates to the database. So the problem that happens is that the replication thread has an update that's going to change data on disk. And a slave has a read transaction open that needs a strongly consistent view of that data. So to support Mvcc, the Postgres slaves don't really know how to do it. So what they know is that they know there's this transaction that needs to be able to see this version of the row. And the replication thread is going to change the data on this row. So what I'll do is I'll just pause the replication thread until the transaction completes. And that's bad because that's preventing replication updates from happening to the database. And if that happens for too long, the slave will kind of fall behind. And so what Postgres does is, in this event, after a certain amount of time has elapsed, it will just kill the transaction that's blocking the replication thread. And that results in you getting lots of queries canceled and lots of errors in database transactions.
Okay, how bad is that? What are the consequences of a transaction being killed? Does this propagate to the user experience?
So typically what will happen is in your application, you'll get like a connection error on the thing. So for Uber's use case, we don't really do any, or at least we don't do very many real-time database updates while you're using the app. So your app experience won't be too affected, but it really propagates into this like delayed task queue layer that I was talking about. And so that's where you run into these issues where we can't bill people for trips or whatnot. And kind of the reason that was happening a lot for us was that to bill a trip, what you need to do is you need to calculate the fare, which involves doing a lot of math on all the trip points. We have to correct the trip points in some cases for GPS error, potentially. We might need to go out to a third-party service to do billing. We might need to send emails. There's like a bunch of things we need to do that can take a long time. And so if the code isn't structured properly and a database transaction is held open during one of these things that can take a long time, that can cause this problem where the slaves start like getting query conflicts with the replication thread. Those transactions start getting killed, and then these tasks start getting killed. They get re-put into the task queue, and then things start backing up, and then we can't bill people, for example.
Okay. So let's talk about how MySQL differs from Postgres. I think the first place to start is how the on-disk representation of data in MySQL compares to that of Postgres. What are the points of comparison there that we should point out?
So there were two things I talked about in the article that I think are like the two really important differences. The first is that in MySQL, secondary indexes don't point directly to where data lives on disk. Instead, secondary indexes contain the primary key information. So there's a layer of indirection in the secondary indexes. The other is that most data in MySQL is not immutable. It can just be changed in place. So when you do an update, in most cases, instead of like moving data around, MySQL will just change the data in place.
Okay, and how does this change the average case performance for lookups between MySQL and Postgres?
So it's not too related to lookups. It's more related to writes. But because there's this extra layer of indirection, in the worst case, MySQL is actually worse than Postgres. But there's this trade-off because it makes writes faster, and there are some other mechanisms that MySQL has, like the buffer pool, that can kind of like offset this read problem.
Okay. What about multi-version concurrency control? How do the strategies differ between MySQL and Postgres when it comes to MVCC? So with respect to MVCC, you still need to have multiple versions of a row around in MySQL. That's just like the nature of MVCC. If there's multiple transactions that need to see multiple versions, you need to keep those versions around. But because MySQL will generally do this update in place in the data, there's less data gets propagated into the indexes when you're doing writes to the database. And what about the write amplification problem? Does this still exist in MySQL? It does not really exist to that same degree, because what happens in MySQL is kind of going back to that previous example I had. You've got this table, it's got 10 columns, and 5 of the columns are indexed, and you're changing a field that's covered by one of the indexes. MySQL needs to like update the row data, and then it needs to update that one index that's affected, but the other indexes don't need to be updated. And so you don't have the same write amplification because your logical changes directly manifest in the same number of physical changes. So what about that problem that you experienced with the bug in Postgres, which was worsened by the replication strategy of Postgres? How would that differ in MySQL?
So what happens in MySQL when you have replication problems, because they still happen, there's still bugs in MySQL, but updates in the replication stream in MySQL, whether you have statement-based replication or row-based replication, they happen more at the logical level. And so in MySQL, you might be missing a row, or you might have 2 copies of a row, but you won't have a problem where an entire index is corrupted because like some bytes are shuffling around a disk. The slaves like logically apply the updates, and so they will keep the indexes in a consistent state even if bad data is being sent over the replication stream.
Got it. So we have started talking about how, it's advantageous for Uber to move to MySQL. Before we get into like how the migration actually took place, were there any other advantages that we haven't discussed yet for Uber's migration from Postgres to MySQL?
Yeah, there are kind of 2 other key things. One was this connection scalability problem. So we just generally found that you can have like thousands of connections open to MySQL. If they're idle, that's not a big problem, but that's a lot more of a problem with Postgres. So that made it a little bit easier to scale our application. And the other one was that we found it's a lot easier to upgrade MySQL versions than it is with Postgres.
Got it. The updates. Okay, that was something we didn't touch on. Yeah, you did mention in the article that there were some issues with Postgres upgrades. So how did this migration actually take place? You decided that, okay, Postgres has these problems, MySQL doesn't have these problems, we're going to migrate from Postgres to MySQL. And then how did that migration actually take place? It sounds really difficult.
Yeah, so we didn't really do it. We did it the other way. So I had mentioned we started off on MySQL and then we switched to Postgres. And we did that as this like big migration. It took like 5 months of engineering effort. It was really scary, and we did it, and there's lots of bugs. And then we were like, we're not going to do that again. So when we decided that we wanted to be trying out MySQL again, what happened was for new services, we tried to move them onto MySQL to test that out, and that was working well. And so kind of for new microservices, they were going on MySQL. And then at the same time, we started developing the schemaless thing, which is kind of this database sharding layer. And so new things were either just like on regular MySQL or they were in schemaless. And then in our monolithic legacy Python codebase, we started just migrating features out and kind of deprecating that. So Postgres still lives on at Uber. We didn't do a full migration, but we tried to move new things to MySQL.
I see. So there's not like an active, aggressive intent to move stuff from Postgres to MySQL. It's more like you'll either move new stuff, or maybe if there's something that is having a acute problem, you can move it from Postgres to MySQL.
Yeah, that's right. I think like the way that I kind of thought about it was we can probably scale our Postgres database 10x without too many difficulties. Like we'll figure out how to do that. We can add new hardware, or we'll get consulting help, and we can do 10x, but 100x seemed kind of iffy. And so if we can migrate the data out fast enough that we won't hit 10x of our current load, then we think that we're doing this migration fast enough and it's okay to keep some of this legacy stuff on Postgres.
Are there some trade-offs you're making here? Like, are there some things that MySQL... I guess you mentioned the schema update, but schemaless is kind of your fix for that. Are there any other costs to switching to MySQL as the main relational database at Uber?
Yeah, so there are a couple of things here that need really good geospatial features. And so Postgres has this PostGIS extension that works really well. That works way better than the geospatial feature in MySQL. So those things are still on Postgres, and there might be one or two other things that have like specialized use cases that are on Postgres, but for the most case, we haven't been missing the features that Postgres provides that MySQL doesn't have.
Okay, so we've talked about schemaless a little bit. Can you tell me more about what schemaless is?
Yeah, so schemaless, at the high level, you can think of it as a database sharding layer for MySQL. So it allows us to partition our MySQL databases into thousands of shards. It also adds this kind of unique indexing feature. So we can have user-defined indexes over things that MySQL wouldn't normally give you indexes for. It also gives you a more flexible schema. So the data that's stored in schemaless, conceptually it's JSON data, and you can add new fields, you can remove fields, and you don't need to do like alter tables. And then kind of the last feature it provides is really strong high availability. So we've kind of made a bunch of extra efforts to ensure that in the event that we've got, say, a rack failure, that we won't lose any data with schemaless and that the application will keep on working.
Okay, so there are also some cases where Uber uses NoSQL databases like Cassandra. What would be a circumstance where Cassandra would be a good fit? And maybe you can talk more abstractly about when people are going to use databases other than the relational database.
Yeah, so the way that I kind of think about it is compared to Cassandra or like React or something like that, schemaless has fewer features, and that's because we're developing it in-house. We started it, we started relatively recently. It hasn't matured to the same levels, but it has some features for Uber that we really need. And so the main one is really, really good persistence and really, really high availability. So if people need really high availability and really good persistence guarantees, we strongly recommend that they use schemaless. On the other hand, if what you need is more of write performance, particularly if you are like caching data, then something like Cassandra becomes a little bit more attractive because Cassandra has better write performance generally than schemaless, and it has some extra features that schemaless doesn't have. So some people really need those features and they rely less on the high availability guarantees that we give with schemaless, and so they would choose to use something like Cassandra in that case.
Okay. So you mentioned that you mentioned that as you scale to 100x, Postgres will probably still be okay. Beyond that, you are really going to want to be on MySQL. Did you do any kind of is it just like a total back of the envelope estimation, or was there any actual math involved there?
So the one thing that was really concrete that we did was we did a bunch of tests with the different connection count settings for Postgres, and we found that the maximum number of connections that Postgres could support was much smaller than what we wanted. And we've got we use PG Bouncer, which is this connection pooler, which can help mitigate the number of connections you have on the back end. But even with PG Bouncer, based on the math we did, we knew that we couldn't scale Postgres to 100x. We also kind of did some math on the size of the wall files in the replication stream. So we knew that even with 10 gigabit links, if we got 100x as many writes to Postgres, we didn't anticipate that we could keep up with the rate that walls would be written to disk.
Fascinating. So we had a show recently about Uber's ring pop, which is this distributed application layer sharding tool. What is the typical interaction between ring pop and the database layer that we've been discussing?
Yeah, so that's kind of an interesting question because they're kind of opposite things to a certain extent. Ring pop is a way to shard your application, distribute it among a bunch of different shards so that each shard is taking responsibility for a different segment of the data. So it's more frequently used for things where the state is mostly persisted in memory in the application. If you have a distributed database that persists stuff to disk, you don't really need that type of sharding. You can just do create lots of instances of the thing and then send traffic to any instance and it will get its data from the database. So as far as I know, none of the ring pop applications at Uber are using MySQL or Postgres or schemaless. But you could use something like ring pop to build a database. And so there are ring pop applications internally that normally they have the data in memory, but they kind of effectively act as a database themselves.
Okay, so I guess that's the salient point, is that with ring pop, you're just saying, okay, we want all of the data for this application to be in memory. We want it to be really fast to access, and the way that we're getting that done in an economical fashion is we're kind of doing a peer-to-peer distribution among the different application instances. Whereas with an application where you're using a database, you might be saying, I guess, okay, there's going to, maybe we'll have a little more latency perhaps with the access of the data, but at least we won't have to do this peer-to-peer sharding stuff. Is that an accurate depiction of the two different types of applications?
Yeah, I think that's accurate. I mean, they're both kind of sharding things in different ways. So like a place that we use Ringpop a lot is in our real-time dispatching system. So the problem would be like, you've got a city, you've got all these drivers in the city, and you've got all these clients who are trying to take trips, and you need to split up that work among a number of different servers. So Ringpop helps you do that, and you're mostly keeping that data in memory. But on the back end, when you've got as many users as we have, or trips, that type of thing, you are persisting the data in the database, and so you don't need to like assign different users to different worker processes. Any worker process can handle the request for any user as long as the database can give back that user.
Okay, so when you're talking here about the Ringpop application of the dispatch system, is the challenge here really that you've got a problem to solve that requires both it requires a lot of data, it requires a lot of computation, and it has to be really fast. Are those the three things that Ringpop is seeking to solve there, that you wouldn't necessarily be able to get the union of those three things if you were using MySQL as the data layer?
Yeah, that's right. And even in that Ringpop system and the dispatching system that we might still use a database, but that's purely to like persist the data in the event of a failure. So if something really bad happens and a bunch of machines crash, you might want to be able to restore the state from a database, but the database wouldn't be used to like be sending it queries to service requests.
That's really fascinating. Okay, well, just to begin to close off, what has been the response to this blog post about Uber's switch to MySQL?
I was really amazed by the response. It was like on the front page of Hacker News, #1 article, which I didn't expect. And then like I felt like every day for a week, I was seeing a different response to the article. I got some people were just like, I love Postgres and you guys suck for saying this. There were some pretty thoughtful responses. I saw that there was a proposal sent to the Postgres developers mailing list for this feature called Warm, which is write amplification something, but it's a feature they want to add to Postgres to mitigate this write amplification problem. So I was pleased to see that, and some of the other features, some of the things I talked about in the article, I got thoughtful responses on how future versions of Postgres will mitigate those problems. So another one is, starting in Postgres 10, I believe, they are fixing this replication problem where you can't replicate between different Postgres versions. And so that would have solved the problem that we have where we have difficulty upgrading Postgres to a newer version.
Could the problem have been avoided if you just hadn't made all those indexes?
It would have been mitigated, definitely. But I think that I think that there's still a fundamental scalability problem where that Postgres isn't as write scalable as MySQL.
Well, Evan, I want to thank you for taking the time. I've really enjoyed this conversation. This has been a very clear depiction of what was initially a pretty complex and hard to understand issue for me. So I hope the listeners have found it to be the same.
Yeah, thank you very much, Jeffrey. I enjoyed talking to you.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow.